So welcome to finding where f is increasing and decreasing. So the idea here, we have seen that if, or the f prime of x being greater than 0 means it's increasing. And similarly, if it is increasing, we should have f prime of x greater than 0 if f prime exists. If f prime of x is less than 0, we have decreasing. And if f prime of x equals 0, then we have a flat horizontal tangent line, right? So if it's only at one point, it won't be constant, it'll just flatten out. So really the only places where we can switch from a negative derivative to a positive derivative is either where we pass through 0 or where the derivative can jump. So the f prime can only switch between positive and negative when it passes through 0. Or when it can jump. And the only way that the derivative can jump is if the derivative is undefined at that point. So note, these are precisely our critical points, right? So either the derivative equals 0 or the derivative is undefined. This is precisely at our critical points. So when it passes through 0 or f prime is undefined, these are precisely our critical points, or the critical values. So we're going to take complete advantage of that. We are essentially going to look for the places where it can switch, and then we can figure out from there. So our method to finding where we're increasing and decreasing, the first thing we're going to do is we are going to find all critical points, or find the critical values. Right? Again, these are the only places where the derivative can switch between positive and negative. So where f prime of x can switch between positive and negative. And so they're therefore the only places where it can switch between increasing and decreasing. Then what we're going to do is we're going to pick a test point sort of in each interval. We'll do this one thing first. So we're going to break our domain, or the interval we're interested in, at the critical values. So we're going to break the domain or interval of interest into multiple subintervals, or into subintervals, with the breaks at the critical values. So with the breaks occurring at the critical values. Then we're going to pick a test point in each interval or in each subinterval. And then we will check the sine of f at each of those test points. So we'll find the sine of f of x at each test point. Then since the derivative can't switch signs until we hit a critical value, so until we go to the end of that subinterval, then we must be find the sine of f prime of x, not of f of x. Find the sine of f prime of x. Since the derivative can't switch signs in the subinterval, there's no critical value to switch signs at, then the entire interval must be that sine. So again, note the entire interval or entire subinterval will have the same sign. Since there's no critical value within the subinterval to switch at. And so then from there, we can determine which subintervals are increasing and which are decreasing. So personally, I think this will make a whole lot more sense once we actually do an example. So we're just going to jump straight into an example. So we're going to determine where the function x cubed minus 12x plus 5 is increasing, and let's go ahead and add that n in. There we go. Where it's increasing and decreasing. So the first thing we need to do is find the critical values. So sorry about that. When we find the critical values, we have f of x is x cubed minus 12x plus 5. So that means that f prime of x should be 3x squared minus 12. And then we are going to set that equal to 0 or undefined. So since this is a polynomial, it's never undefined. So we only need to figure out, we only need to solve where it's equal to 0. So this 3x squared minus 12, we can factor out a 3. We're left with x squared minus 4 on the inside. And then x squared minus 4 is x plus 2, x minus 2. So we have 3 times x plus 2 times x minus 2 is equal to 0. And then at this point, again, we have x plus 2 equals 0 or x minus 2 equals 0. This first one will give us x equals negative 2. And the second will give us x equals positive 2. So we have our critical values of x equals negative 2 or x equals 2. The next thing we want to do is we're going to break our domain up into subintervals at the critical values. And so what I typically do is just draw a number line. So we're going to break into subintervals. So we're just drawing a number line. X is what is going to be marked along the bottom. So the only points of interest are at x equals -2 and x equals 2. And then f prime of x at those points we know was 0. I like to just keep record of this because as we keep going in this class, it'll be useful to keep record of what type of critical value we were working with. And so our subintervals, we have from -∞ to -2 is our first subinterval. We have from -2 to 2, and we have from 2 to infinity. Now, personally, I don't usually list these. I usually just draw the number line, and that's what works for me. But if it is helpful for you to write out the intervals, then go for it. Now, what we're going to do is we're going to pick a test point in each of those intervals. So we need a test point in each subinterval. So once again, I'm just going to draw my number line. So again, x is down underneath. So at -2 and 2, f prime was 0. And so the test points that I'll pick, I might as well pick x equals 0 as a point of interest, and then maybe pick x equals 3 and x equals -3. You can pick any point you want as long as it falls within that subinterval that we have found. And our subintervals are all open. Right. So again, if you prefer to think of this in interval notation, so what we did was for -∞ to -2, we picked x equals -3. For -2 to 2, we picked x equals 0. And for 2 to infinity, we picked x equals 3. I'm actually going to change these colors to match what I did above. So let's do those in purple. So we have x equals -3, x equals 0, and x equals 3. And at each of those values, we're just going to see what f prime of x looks like. So now we need to find the sine of f prime at each test point. So again, just a reminder that f prime of x was equal to 3 times x plus 2 times x minus 2. There are a few ways you can do this. I'll go ahead and show you both. One option is literally just to evaluate, like, we also said this was 3x squared minus 12. Right? So one option is to literally just plug in x and evaluate. And the other one is to just kind of look at the factored form and see what sign each factor would have. So if we do x equals -3, option 1, we would do f prime of -3 is equal to 3 times -3 squared minus 12. which would be 27 minus 12, or 15. So this is positive. At x equals 0, we would have f prime of 0 is equal to 3 times 0 squared minus 12, or negative 12. So we have a negative. And then at x equals 3, we have f prime of 3 is equal to 3 times 3 squared minus 12. Again, 27 minus 12, or 15, so we have positive. So I would create my number line. We have negative 2, 2. These are both 0 for f prime of x. This is x. We had our test points at x equals negative 3, 0, and 3. And we found at each of those points, first we had a positive derivative, then a negative derivative, then a positive derivative. Now again, because the derivative cannot switch signs until we hit a critical value, we know that entire subinterval is that sign. The other format that I would take for these, option 2, we'll just do off to the side. For x equals negative 3, if we did 3 times negative 3 plus 2 times negative 3 minus 2, this is a positive times a negative times a negative, so we get a positive out. Sorry about that, there we go. For x equals 0, we would have 3 times 0 plus 2 times 0 minus 2. So we would have a positive times a positive times a negative, or get negative result. In this last one, we have 3 times 3 plus 2 times 3 minus 2. Positive times positive times positive, we get a positive result out. As you get more comfortable with these, you will likely not even write in the x values necessarily. You will just write out, oh, positive times negative, or whatever format it is. So you're welcome to use either of these formats. They're both perfectly acceptable, or either of these methods. Right? You can either just plug in the value and evaluate, or you can just figure out each of the factors, is it positive or negative at that x value, and figure out what the ultimate sign would be. All right, so here is our number line. The last thing we're going to do is we're going to determine where the function is increasing and decreasing. So at this point, we have a number line. We know what's happening with x. The points of interest were negative 2 and 2. F prime of x was 0 at those 2 points of interest. The derivative was positive before negative 2. Then it switched to negative. Then it switched to positive. No, I didn't write in the test points here because they're not really needed, but you certainly could write in the test points. Now what I'm going to do is I'm going to write f of x up top and just draw what's happening. So a derivative being positive tells us the function is increasing. Derivative being 0, we flatten out. Then we decrease. I'm going to just do an arrow so that it doesn't look like a negative sign. Then we flatten out, and then we increase. Okay, so positive derivative, increasing function, negative derivative, decreasing function, 0, we're flat. So just from this, we know that it is increasing on the open interval -infinity to -2, as well as on the open interval from 2 to infinity. And then it is decreasing on the open interval -2 to 2. So usually when I do these myself, I show the work for finding the critical values. I draw this number line, and then off to the side, I'll do my test points or just what would happen in the interval itself for finding the sines, and then everything else is just on the same number line. So in the future, in the next video, I'll do a couple more examples, and I will just show everything sort of on the same number line as we go.